Okay, so I'm just going to get started because I'm sure by now you guys are probably tired of hearing my voice. So any extra things I have to say, I'll just include it at the end of the video so you could just skip it if you don't want to hear it. But anyway, 7x says, for the following reactions, draw one stereoisomer of the product of each of the following reactions. Show correct stereochem. So the first thing you have to do when you're looking at these types of problems is figure out, okay, well, what kind of reaction is this? In general, when you see a conjugated double bond being added to another double bond under heat, that's a good sign that it's going to be a Diels-Alder reaction. In general, honestly, if you see heat and two things being combined together, it's most likely going to be a Diels-Alder reaction. But just really quickly, let's go over the general format of a Diels-Alder. You're going to have the conjugated double bond in a cis-diene, and then the other double bond with something coming off of it 9 times out of 10. So as you can see, these double bonds are cis to each other. However, the ones that they gave us are trans. So you actually have to do this problem, you have to be able to convert the trans to the cis formation. So I'm going to show you how I personally do that. Okay, so the first thing I like to do is I like to draw the template as I know it's going to look. And then I like to go in and fill in the H's on my original trans diene. So looking at the first double bond, I'm going to draw in the H's. Whenever you look at a double bond, there's going to be two things coming off of either side, right? So if the carbon is coming down this way, the H has to be up here. If the carbon is up here, the H has to be down here. There's no other space for these molecules to go because this is sp2, or these are sp2 carbons when you have an alkene. So if we see the carbon coming down here, the only place for the H to go is going up. Okay? So likewise, on the second half of the double bond on this carbon here, if this carbon is going up, the only place for the H to go is down. All right? So now keeping that in mind, we can go ahead and figure out where this methyl is going to go on our diene. So if our first H is going to be here, going away, because the only place we have is down or up, and in this case, they already put the carbon down, or the rest of the molecule down, so the only place for the H to go is up. So now on the other side, because these H's are trans to each other, one is going up and one is going down, you have to make your H's trans to each other on your diene. So if this H is going up here, the other H has to be going down. Does that make sense? So that lets you know that the only place for the methyl to go is up or away from the center of the diene. Hopefully that makes sense. If anybody has questions, you could definitely ask me. But now let's look at the other double bond. So again, we have a pair of trans H's because one is going to go up and one is going to go down based on where the other carbons are located. So going over to this double bond here, we're going to have to put the H down because the rest of the carbon molecule or the rest of the chain is up. So you can go ahead and fill this H down. Because these are trans here, we have to make sure they're trans here. So the other H is going to go up. And that lets us know that our methyl is going to be going down because that's the only other place it can go. So redrawing that, it's going to look like this. And there are other ways to, all right, that's kind of ugly. Let me try again. There are other ways to do this. A lot of people will just visualize it. They'll mentally rotate this over to see what it would look like. And if you bring this carbon over here, you'll see how the methyl would be pointing down. But, I mean, it's up to you if you want to do it that way. If you're really good at visualizing, then go for it. I personally am not. It took me a while to get it that way. So I like to use the trans and cis H's. Okay. So now we can go ahead and just do our regular Diels-Alder. Because you only have one functional group on your... okay. So if you have a functional group here... and here, you have to do the resonance, but if you only have one here, you don't have to do the resonance. So keep that in mind to save time. So you can just go ahead and do the Diels-Alder as we normally would. Really quickly, I'm going to repeat the key that I use just in case people forgot or want a reminder. So anything that's pointing away from the center of the diene is on a dash. Anything that's pointing towards the center of the diene is on a wedge. So conversely, that means... this would be on a wedge, this would be on a dash. For the dienophile, anything that's pointing towards the center is on a dash. Anything that's pointing away from the center is on a wedge. Again, conversely, that means this would be on a wedge. this would be on a dash. So this is the key that I use whenever I do my Diels-Alder reactions, and it usually works for me. Okay, so now we can get started. I like to draw in the template of the product first, so numbering my carbons, this is 1, 2, 3, 4, 5, 6, and then you know you're gonna have a cyclohexane with a double bond between 2 and 3. So 1, 2, 3, 4, 5, 6, and this is how it's always going to be. Reason being is because when this bond comes down to form the new bond of the ring, that pushes this one up, this forms the new bond of the ring, and that pushes this double bond down to form the double bond between 2 and 3. You don't have to memorize the movement of electrons. He never is going to ask you to demonstrate it. But in case people were wondering why is the format always the same, that's why. So let me erase really quickly. So on 1, we have a methyl and it's pointing away from the center. So you can go ahead and draw your dashed methyl off of 1. Okay. On 4, we have a methyl and it's pointing again away from the center. So that's going to be another dashed methyl off of 4. And then on 6, we have a nitrile and it's pointing towards the center. So that's going to be on a dash. Okay. And that is going to be the answer to this question. I'm going to redraw it neatly for you guys. Give me 1 second. Okay. Okay, so that is the answer to 7XA. Hopefully that all makes sense. Feel free. Okay, so for part B, we have another Diels-Alder reaction. So again, we're given the diene in the transformation, and we're going to have to convert it to cis. So the way that I do it is I just go ahead and draw this in. And I like to always draw the SH pointing away from the diene, because if you draw it in like this, it's going to be really confusing. So just go ahead and do it the way that I'm doing it, honestly. Because in this case, even if you flip it over, like if you move this over, like visually, the SH is going to be like in the center, which is a little bit more confusing. You want the SH like on the outer part of the diene. Okay. So now we can do the same thing with the H's. So on this side, we're going to go ahead and fill in the H. So the H is going to be trans to the SH. We can see that the SH is going up and the H is down. So on this side, we see the SH is up. So the H has to be on the other side of the double bond going down. See how these kind of match each other up here and down here? So that will help you figure out where the methyl is going to go, because there's only 2 places you could go on a side of a double bond, up or down. The methyl is going to be going up or out of the diene. And then we can go ahead and do that with the other side, drawing our H's. Okay, so we have H's that are trans to each other again. So on this side of the diene, we're going to draw the H down, because the rest of the molecule is already going up. On the other side of the diene, you're going to have to draw the H up to get them trans to each other. And then that only leaves one place for your methyl to go, which is down. So redrawing our diene, it's going to look like this. Pretty similar to the last question, except now we have an SH on it. Okay. And our dienophile. In this case, once again, you don't actually have to draw the resonance. Reason being is because this functional group here is between carbons 2 and 3, and it's not going to get any stereochem in the product, because between carbons 2 and 3, you're going to have a double bond. So you don't actually have to draw the stereochem for this one, or like the resonance, whatever I mean. Sorry, not stereochem, resonance. So you can just go ahead and actually start your Diels-Alder exactly like this, and you will get the right answer. So let's go ahead and draw the basic. If the SH had been here, for example, instead, then you would have to do the resonance, because this carbon will have a chiral center in your product. But because between 2 and 3 there's a double bond, you don't, like, there's no chirality, so it doesn't matter if SH is on a wedge or a dash, because it won't be on either. I hope that makes sense. When we do the product, you'll see exactly what I mean. So 1, 2, 3, 4, 5, 6. Okay, so between 2 and 3, you're going to have your double bond. You can go ahead and just draw your SH coming off of it. Because this is an sp2 carbon, it's not going to be chiral. You're not going to have a wedge or a dash. So this is the point I was getting at. It's not going to have any chirality here. So now off of carbon 1 of the diene, we have a methyl, and it's pointing away from the center of the diene. So away from the center of the diene means that you're going to have a methyl on a dash. On carbon 4 of the diene, you're going to have a methyl pointing away from the center once again. So you're going to have another methyl on the dash. And then carbons 5 and 6, off of 6, you're going to have a carboxylic acid. Because you don't have to draw the resonance, you could leave it the way it is. And since it's pointing towards the diene on a dash, towards the diene, you're going to put it on a dash. So, oops. It's hard to draw these on a dash. Okay, so that's what your answer is going to look like for this one. I'll go ahead and redraw it neater up here. Oops, wrong carbon. Hold on, did I put it on the wrong carbon here? Okay, so again, we have a Diels-Alder that is very similar to one that was on the Primoc. But the difference is, notice how here he didn't say to use excess of the diene. He didn't say that. So if you don't have excess of the diene, you can't react this twice, even if there is a triple bond on your dienophile. So in this case, make sure you only do the reaction one time, not twice. And I know a lot of people are just going to see it and immediately do that and probably react it twice. But it's very important to make sure that you read the directions for these types of problems, because he will try to mess with you, especially because he knows a lot of people have the old exams. Okay, so with that in mind, let's go ahead and start. So what ends up happening in this reaction is when you do the Diels-Alder, these two carbons are going to pop up and form a bridge. And then these carbons are not going to, or these functional groups, this carbon technically, these two carbons are not going to have any chiral centers because they're going to be sp2 hybridized. Because like I said, you're only going to react it once. So you can go ahead and draw your product ring and number. So 1, 2, 3, 4, 5, 6. So this is going to get rid of one double bond on your dienophile. So between 5 and 6, you're still going to have a double bond on your product. Between 2 and 3, oh, oopsie, I didn't mean to draw it like this. I was getting ahead of myself. It should have been like this. So between 2 and 3 in your product, you're going to have a double bond, so you can go ahead and fill that. Between 1 and 4, you're going to have the bridge coming off. And then your NO2s are going to be coming off of 5 and 6. Like I said, because these are sp2 carbons, you're not going to have any chirality there, so they're just going to stay as is. I forgot to number my carbons, but we've done this a couple times, so hopefully this all makes sense. So this is what your product is going to look like. I'll redraw it neater in the box. Okay, and that is the answer to part C. Okie dokie. Last but not least, we're going to have a intramolecular Diels-Alder. So we've done this a couple times now, but just to review, I will go ahead and do it the way that I do it. So as usual, I like to number my 1, 2, 3, 4, 5, 6, because I know this is going to be the formation of one ring. And then I like to go and number the rest of the carbons in a different color, or like however you want to do it. 7, 8, 9, because these are going to pinch off and form a second ring. Okay, so now looking at our product, we can go ahead and do the 1, 2, 3, 4, 5, 6. As usual, you're going to have the double bond between 2 and 3, and there is a CN coming off of 6. If you move, actually, you know what, let's just do it in the trans-cis way. But technically, if you just rotate this up a little bit, right? So at least this is the way I do it. I just visualize, like I rotate the dienophile a little bit up. So it's going to look like this. You could pretty much see that the CN is going to be pointing towards it if you just move it up a little. So that means your CN is going to be on a dash. However you want to do that is up to you, but I personally just visualize it in this case because it's like pretty much already given to you. Okay, so back to what we were doing, 7, 8, 9. So you can go ahead and draw your CN on a dash off of 6. And there's no methyls coming off of our diene, so we don't have to worry about that. We just have to worry about the rest of the ring. So off of 4, there's a carbon 7. Oops, that's a Z. 8, 9. And this is what the second ring is going to look like, so that's going to be your product. Okay, hopefully that made sense. In general, like, whatever comes between 4 and 5 is going to pinch off and form a second ring. So just make sure that you're careful about that and you practice these a couple times. All right, so redrawing the product neatly. It's going to look like that. Okay. So multiple choice 1 in very poor English asks us to rank the pKa's of the hydrogens in the box in order of decreasing pKa. So that means your highest pKa is going to go first and your lowest pKa is going to go last. Really quickly, I guess we should make this note that high pKa is the basic ones and low pKa is the acidic ones. So they want us to rank these in order of most basic to most acidic. Yep. And very quickly, I'm going to go ahead and fill in the actual pKa's for all of these, and then I can go over how you would do this if you didn't happen to know the actual pKa's of all of these. So number 1 is going to have a pKa of around 45. Number 2 is going to have a pKa of around 5. 3, again, a pKa of around 5. 4, pKa of around 5. And I'll go over how you can rank between 2, 3, and 4. 5 is going to have a pKa of about 35 or 36. And then number 6 is going to have a pKa of about 25. So the way I would do this if it was me, I would honestly start with the carboxylic acids first, just because there's 3 of them. So when you're comparing the 3 different carboxylic acids, you want to look at what is bonded to it as well. So 2 is just a regular carboxylic acid. 3 has a chlorine on it, and 4 has a methyl on it. So when you're thinking about these, the differences between them is chlorine is acidic, electron withdrawing, and contributes to the inductive effect because it is withdrawing electrons towards itself. Okay? So that being said, since it's able to pull electrons towards itself, when you lose that H on the OH, you're going to be left with the O anion. And now you have an extra pair of electrons that you have to handle. If you have a group that handles electrons well, like a Cl on your molecule, that makes it more stable when you add extra electrons. So 3 is going to actually be the most acidic because the Cl helps the molecule resonate an extra lone pair better. And the better that your molecule is able to resonate lone pairs, the more likely it is to give off hydrogens. So 3 is going to be the most acidic. So you can eliminate any answer choices where 3 is not at the end. So that's B, C, and D. And now, I'm going to erase this. We can compare 2 and 1. So the difference between 2 and 4. So the difference between 2 and 4 is that 4 has a methyl on it. And as we all know, methyls don't really like to give off H's on their own. So that makes methyls relatively basic. So when you add a basic substituent to your carboxylic acid, you're actually going to increase the pKa. Increases pKa. So between 2 and 4, the only difference is that addition of the methyl. So that means 4's pKa is actually going to be higher than 2's. So the answer choice that you're looking for should have 3, 2, and then 4. Both A and E have that, so we're not able to eliminate anything yet. Okay, so I'll put over here our ongoing ranking. So now we're going to be looking at 1, 5, and 6. Okay, so 5 in general is relatively basic, so you know that's not going to come next. So I would just put 5 in the corner for now. Between 1 and 6, 1 is an sp2H, which is very, very, like, as you guys remember, I told you if you ever see this is very, very, very unstable, very unlikely to happen. So from just experience, you would know that 1 is going to be your least acidic, just because if you've never seen something like this, right? For example, if you had your amine, you can definitely see an amine that's like this. It's not as common, but it does happen. Okay, NH2, for example, like we've definitely seen that. And 6 is an alkyne, and we all know that alkynes are being used to make alkynyl anions. So keeping that in mind, if you're able to pull the H off of the alkyne to make an alkynyl anion, you know that probably has a relatively low pKa if it's something that we do pretty commonly. So now we can go ahead and rank these just based off of experience. We know that the alkynyl anion is pretty common, we've seen it a couple times. So just using reasoning, you could put that next. NH3 is very basic, so that's going to come next. And then finally, you're going to have your sp2 carbon. That would not want to give off an H ever because, as I told you guys, this, very bad. This, also very bad. Anytime you see a charge directly on a double bond, that's a really, really unfavorable thing, and we've never seen it. I did mention the carbocation on the double bond before, but I never specifically said the anion. But in general, charges directly on double bond is a boo-boo. If you want to go ahead and write these pKa's down, since you guys don't have to memorize everything, I would go ahead and do that. But logically speaking, that's how I reasoned through this question without knowing the pKa's at first. So the answer is going to be A, 1, 5, 6, 4, 2, and 3, where 1 is the least acidic because that H is very unlikely to come off, and then 3 is the most acidic because you have the Cl that allows for the inductive effect, that allows for the resonance of electrons, so the H is more likely to come off. Okay. Number 2 asks, how many of the following structures are Lewis acids? So what makes a Lewis acid, or the definition of a Lewis acid, is, I know we all know it as just an electron acceptor, but it's a little bit more than that. A Lewis acid has to have a orbital, or an orbital, let me use English, an orbital that is free to accept electrons. Okay? So it's a little bit more than just an electron acceptor. It also has to have an orbital for it, right? So let's go ahead and look at the compounds that we have. I'm going to erase this definition. Okay, so number one, or I'll number these. So 1, 2, 3, 4, 5. Oops, that's not a 5. Okay, so 1 is going to be a carbon that is missing the H. So in this case, this carbon is bonded to, oh my goodness, not H's. It's bonded to the methyl, the other side, and the other side of the chain. It literally has an orbital open where the H would normally go, and that is what's giving it the plus charge. So because it has an open orbital that can accept electrons, this is going to be a Lewis acid. So that's one of them. Now we can look at the NH3+. I know it's very tempting to say, okay, yes, this is a Lewis acid because it has a plus charge, so it's going to want to accept electrons. But the thing with Lewis acids is, like I said, they have to have a free orbital to accept electrons, right? So NH3+, if you draw it out, does not actually have a free orbital because it can't expand its octet. You can only have your N bonded to 4 things and then, okay, bonded to 4 things, or like when I say that, it could also have a lone pair. Like that counts as something that it's bonded to, right? So because N can only have 8 electrons around it, whether it's in bonds or lone pairs, it can't accept any more electrons in this case. It would have to donate an H. So this one is actually not a Lewis acid, although it's very tempting to pick it as one of them. So not a Lewis acid because no free orbital to accept a lone pair. Oopsie. Okay. So now we can look at number 3. Oopsie, let me do that in black. So on this side, we have a CH3 bonded to an OH. Again, as we can see, there's no free orbitals anywhere for anything to accept electrons. The C has 4 bonds, so it has a full octet. The O has 2 lone pair and 2 bonds, so again, a full octet. And honestly, there's no reason that this would want to take a electron anyway, because if the O were to take even more electrons, it would be anionic. So it's not as favorable as just being neutral. So in this case, 3 is not going to be a Lewis acid. Okay, looking at 4, AlCl3. This is actually one of the common Lewis acids, so hopefully you guys remembered that. Right off the bat, you don't really have to draw it out. But the reason this is a Lewis acid is because it actually does have one orbital open, because Al is only bonded to 3 things here. So it has one orbital open, and because it's a metal, it's more likely to accept electrons. So yeah, AlCl3 is one of the most common Lewis acids. Has open orbital. Okay, looking at number 5, BF3. This is another really common, ooh, I forgot to put the check. BF3 is another really common Lewis acid because same situation that you have the open orbital here and it likes to accept electrons. So yeah. A lot of this was just Gen Chem knowledge, but I think the NH3+ is what might throw some people off. BF3, common Lewis acid. So out of these answer choices, 3 of them are Lewis acids, so that means the answer to number 2 is going to be C. Okay, so 18 asks, how many of the following changes would make the rate of this reaction go faster? And addressing leaving groups, I actually did look into it really quickly. I went to find my notes. So this is the order of leaving group ability. So I is going to be your best, then Br, then Cl, and then F. So just remember that and you'll be good to go. Okay? So number 1 says changing Br to Cl. So changing a good leaving group to a not as good leaving group is actually going to make the rate of your reaction go slower. So that is not one of our answers. Changing Br to I, so changing a good leaving group to an even better leaving group, will increase the rate of your reaction. So 2 is one of these that are true, or that do make the rate of the reaction go faster. Number 3 says increasing the concentration of R2-bromobutane. Okay, so for this kind of statement, they're asking you whether this is a SN1 or SN2 reaction. So this is pretty easy to figure out because you see an inversion in your product. So that is the most obvious way of being able to tell that this is SN2. Also, SH is negative. It's in its anionic form because you see the Na plus is paired with it. So that also tells you that it's SN2. I know you see H2O as a polar protic solvent. However, sometimes people include H2O under the arrow as a way of saying this is a counterion that is formed throughout the reaction. So don't worry too much about the H2O. Focus more on the nucleophile and the stereochem, and you'll be able to address which reaction it is really, really easily. So number 3 says increasing the concentration of R-bromobutane. Okay, SN2 reactions, the rate depends on the nucleophile and the substrate. So yeah, that actually would help the reaction because you're increasing the concentration of the substrate, and that's going to increase your rate. Okay, now increasing the concentration of water. This is pretty much useless. You wouldn't want more polar protic solvent in an SN2 reaction, so that is going to decrease your rate, and that's bad. Okay. Number 5 says increase the concentration of sodium hydrosulfide. So this is your nucleophile. This is this that they're referring to. And as you can see from your rate law, increasing the rate of your nucleophile is going to increase the rate of your reaction. So this is good. Okay. Changing water to methanol. So no, that is not going to increase the rate of your reaction because you're changing a polar protic solvent to an even more polar protic solvent. So this is bad. Methanol is more likely to donate protons than water will because it's more acidic. 7 is changing water to DMF. That's what dimethylformide is, so DMF. And as you guys know, that's one of our polar aprotic solvents, and that will increase the rate of the reaction because SN2 prefers polar aprotic. So 4 of these would make the rate of reaction go faster, so the answer to number 18 is going to be C. Okay guys, so for number 4, this is actually such an old question that he doesn't use a lot of these reactants anymore, so you don't have to worry about it, but just in case you were one of those people who wanted to know the answer, it was 3 of them, and it was the first one, the second one, and the fourth one, but like I said, he doesn't use these reactants anymore, so don't worry about it, you guys can just skip it. Okay, so number 19 says, in the reaction shown below, indicate whether the reaction rate will increase under the conditions listed in X, Y, and Z. So very similarly to what we did to the last question, you want to distinguish whether this is an SN1, SN2, E1, or E2 reaction, right? So we're going to first compare the reagent and the products. So we see that we start with our Cl, our leaving group, on a wedge, and we finish with our nucleophile being added on a dash. Not to mention, it's the only major product. So when you get inversion and only one product, that is characteristic of SN2 reactions. To strengthen the support that this is an SN2 reaction, you have a strong anionic nucleophile and a polar aprotic solvent. So this is an SN2 reaction for sure. Okay? So now we can look at the conditions and see whether or not this would increase the rate or decrease the rate of reaction for an SN2. So, increasing the amount of DMSO solvent. That's going to increase the rate of reaction because you're giving more polar aprotic solvent. So you can eliminate anything where it says that X will decrease the rate of reaction. Oops. So eliminate B, D, and E. Okay. Y says change the solvent from DMSO to ethanol. So you're going from a polar aprotic, which is characteristic of SN2, to a polar protic, which is characteristic of SN1. So that is definitely going to decrease the rate of your SN2 reaction. So right off the bat, you can eliminate C, and the answer is A. So you don't really, for this question specifically, you don't have to remember which of the leaving groups is better, but just a reminder that I is the best, then Br, then Cl, then F, okay? So the answer to number 19 is going to be A. Okay, so basically multiple choice 6 is asking you, what are the reagents and products in the following reaction sequence? So in order to specifically find reagent P, we have to look at the starting material and the product and see what has changed. So in our starting material, we start with a double bond and a methyl on one side. Okay, so now when we look at the finishing material, Q, you see that an OH has been added to the less substituted side and tied to the CH3, or to the methyl. So now, keeping that in mind, we can look at the reagents that they gave us and see which one of them is going to give us the anti-Markovnikov addition of an OH. So A is just treating it with acid, and what this is going to do is give you Markovnikov addition of an OH, and then rearrangements are possible. That's not English, but, you know, I'm trying to shorthand it. So then B is the oxymercuration reaction, and this is the Markovnikov addition, oopsie, without any rearrangement. And then C is the same thing, the oxymercuration reaction, and then D and E are the hydroboration reaction, and these are the anti-Markovnikov addition of an OH across a double bond without rearrangements. So what we're looking for is the anti-Markovnikov, because you want one where the OH is getting added to the less substituted side. So now you know that the reagents for P are going to be either, well, not either, it's going to be the hydroboration reaction. So your answer is going to be either D or E. So then what I did is I just filled in the hydroboration up here, H2O2, NaOH. And then now we can move from Q to R, and we can try to figure out what the product for R is. So they're telling us that the second reagent that we're going to use is PBr3. And what PBr3 does, I'll write it down here, is it is going to replace OH with a Br in an inversion reaction. So if it's replacing the OH with a Br and it's inverting the stereochem, your product is going to look like this. Okay, so now you just want to look for that product in these, and you could see that that is the answer to, or that is the answer from letter E. Okay, so number 7 is going to ask us, which of the following are the two major products of the reaction shown below? So in general, you have to know what NBS does. NBS is going to add a Br, a allylic, to a double bond. But when you're thinking about the position it can add, the Br with the double bond in this form can either add here or here. And as we remember from the radicals lecture, Br prefers to have the more highly substituted side. So this is going to be the major product, and this is going to be the minor product. However, when you're actually doing the mechanism, the double bond can resonate, so then the Br can add in different places. So there's two major products. There's the major product of the double bond here, and then there's the major product of when the double bond resonates. So in order to answer this question, you actually have to go in through the mech and do the resonance of it. So let's go ahead and do that. So right off the bat, you know one of the major products is going to be this, because it's the more highly substituted allylic addition of the Br with the double bond in this place. So you know one is going to be one of the two major products, so you can eliminate anything that doesn't have one in it. Now, for the first step, you're going to generate the Br radical. I've already went over this in the radicals lecture, so if you guys want to look at those notes, go ahead and do that. But we'll go into the propagation part really quickly, because this is the more important side of the mech anyway. So propagation, as you guys already know, has two parts. Part 1 is going to be the bromine abstracts an allylic hydrogen. So, as we can see, there's two allylic hydrogens on our starting material. You have one here and here. In general, it's more favorable to abstract the more highly substituted hydrogen because that will give you the more highly substituted radical. So that's what we're going to do. Okay, so you get your radical Br from the initiation step when NBS reacts with itself under the presence of light. So really quickly, we're going to draw in our H. And one of the electrons from the H is going to form the bond with the Br, and one of the other electrons from the H is going to form a radical on that carbon. So the product is going to look like this. And then in the second step of propagation, you're going to get the Br added to where the radical is. So the addition of the Br to this radical gives you major product 1. Whoops. Okay, so I'm going to call this prop part 2. Gives you major product 1. Okay? But what you also notice is that whenever you have extra electrons in double bonds, there can be resonance that can occur. So using the molecule here, we can actually have a resonance structure. So let's go ahead and draw that. Okay. So this radical is going to come and form a double bond. One of the electrons from the double bond is going to come down and form the double bond, and one of the other electrons is going to stay on this carbon, forming a new radical. So the resonance is going to look like this. So this will give you major product number 2, because now a Br can also add to this radical. So I'm going to call this propagation part 2, because that's what's going to occur here. And then this will give you this answer. And this is your second major product for this question. So normally they only ask you for the major product, and that's going to be this one. But every time you do these, if there's resonance possible, there's going to be 2 major products technically, because you have to resonate it. So now looking back at our answers, we see that our second major product here, let me redraw it a little bit better. Okay, so our second major product redrawn because I was running out of space. Oops. Is actually going to be number 3 over here. So this is major product 2. And the answer is going to be 1 and 3, and that's letter D. Okay, so really quickly, I think I'm going to decide to actually go through the mech of NBS because I know some people weren't there for the radicals lecture and who knows what their reasons may be. So if you're not interested in that, you can go ahead and skip along, but I'm just going to do the entire mech in case people have questions. I think in the last one, I did the mech for BR2 under the presence of light, so it's probably good that I do NBS in this one. But yeah, the answer to number 7 was D, just so you guys know. Okay, so allylic bromination using NBS. Okay. So step 1 is the initiation step. And this is the homolytic cleavage within the NBS molecule under the presence of light. Okay? So light, 9 times out of 10, is either going to be represented as light or HV. So in parentheses, I'm going to write HV. So here is NBS, and I do think it's really, really important to know the structure of NBS because he usually asks for it on the final. So NBS under HV, and what's going to happen is that the N is going to take 1 electron and the Br is going to take another or the other electron, and this is going to generate your radical Br. So your products are going to be the radical Br and the radical N in your NBS. Okay, so let's go through step 2. Okay, step 2 is propagation, and there are 2 parts to propagation. Okay, so part 1, like I said before, your radical bromine is going to abstract a allylic hydrogen, leaving behind an allylic radical. So this is the step where resonance can occur. And it's also important to, I can't even spell occur, Jesus Christ. And it's also important to note that you want to pick the hydrogen that will give you the more highly substituted radical, because that will give you the more stable product, which is going to form more often than the less stable product. Okay, so now I'm going to erase and go ahead with my example. Okay, so the alkane chain or alkene chain that I'm going to use is just a simple propene, and we're going to react it with the radical Br. The Br is going to pull off an allylic hydrogen. So the H is going to come here. 1 electron is going to come and make the bond with Br, and the other one is going to return to the molecule. So your product is going to look like this. Oopsie. I can't draw today. Plus HBr. Okay, so that's part 1 of propagation. I'm going to now erase. Okay, so part 2 is that the allylic radical, and allylic, just as a repeater, just means 1 space next to the double bond. So the allylic radical reacts with Br2 to form another allylic Br. Okay. So in our example, we have this plus Br2. So one of these BRs is going to form a bond with the radical, and one of them is going to take the extra electron. So your answer will look like this, or your product will look like this. And these are the 2 steps to propagation. These are the most important. And then the last step is going to just be termination. And all you have to do in termination is bond every single radical together in every way that you can think of. So really quickly, termination, bind all radicals together. So I'll give you some examples that I have in my notes really quickly, but I am missing a few because I did this quickly. He will never ask you for the termination step anyway because there's just too many different products that you can have. Okay. Okay, so that is it for the mech for NBS. Number 8 asks, for each of the following pairs of the E2 reactions, select the one that occurs with the greater rate constant. So the first thing to note is that a greater rate constant means that you're going to have a faster reaction. And you get faster reactions when the conditions are favorable. Okay. So let's go ahead and check these out. So for number 1, the only difference is between your alkyl halides. So on this side, you have CH3, CH2, CH2Cl. But on this side, you have CH3, CH2, CH2I. So they're basically asking you in this question if you know what the best leaving groups are. So I'll give you guys the list of the best leaving groups to the worst leaving groups. So best LG is I, then Br, then Cl, then F is the worst leaving group. So with that in mind, you know that the substrate using I is going to be better than the substrate using Cl because I is a better leaving group. So for the first part, 2 is going to be the choice. So now you can eliminate any of the answer choices that don't have 2 as the first one. Okay, so I'm going to erase. Looking at the second set of comparisons, you are comparing the nucleophile in this case. So you have CH3O minus on the left or CH3S minus on the right. So although technically in general CH3S minus is a better nucleophile than CH3O minus, the trick here is that you have to know that E2 reactions occur in polar protic solvents. So what does that mean? These are solvents that hydrogen bond. And as we remember, a lot of times when you're using polar protic solvents, your nucleophile is going to also be your solvent. So the only one of these that's polar protic is the CH3O minus. So for that reason, although CH3S is generally a better nucleophile, in a polar protic solvent, you want something that can H bond and is going to work well with water. So in that case, CH3O minus is the better nucleophile when compared to CH3S for an E2 reaction specifically. So now you can go ahead and eliminate any of the answer choices where 3 is not the next option. So you are left with C as the right answer, but we'll go ahead and look at the last comparison as well. Oops. So in this case, they're asking you where is the location of the halogen best. So they're basically kind of asking you how does the E2 reaction work. So in general, we'll do this in context of the first one. When you're doing an E2 reaction, you're going to be pulling off an H that is going to form a double bond and then kick out the Br. So on this side, you can pull, or like on the first side here, you could pull off the H closer to the benzene. So the OH can come and pull this H off. That's going to form the double bond. That's going to kick off the Br. And then you have a conjugated double bond to the ring. Ooh. So this double bond can actually resonate with the ones in the ring. Now when you do the same thing with the Br on the other side, or this Br I meant, it's kind of hard to like explain this without being able to like point or show you guys what I'm talking about. So sorry if it gets a little confusing, but using the second option, or option 6, if you pulled off the H here, you would get, so we'll say the OH pulls this H off. This forms a double bond, kicking the Br out. You would get your double bond here, and this is not conjugated with the ring. So in general, it's more favorable to use, let me use a different color. It's more favorable to use this one because you can end up with a double bond that's conjugated with the rest of your double bonds. So all of these 4 can resonate with each other, whereas only these 3 can resonate in the second one because this one is too far away. So 5 is the better answer than 6, and of course that matches with C, so you can go ahead and circle C as the right answer for number 8. Okay, so number 9 asks us, what sequence of reagents is required to accomplish the following transformation? So basically this is kind of a synthesis question, except because it's multiple choice, they're giving you a little bit more of a hint or like some help. So the way I did this is I did a little bit of retrosynthesis. The only way we know how to get a OH onto a molecule is from a double bond. So you know you're going to have to at some point add a OH from a double bond. And because your OH is terminal, you know you're going to have to use an anti-Markovnikov addition without rearrangement. So you can go ahead and just write in the hydroboration one here. Okay, now the only thing we know how to add straight up to an alkane is a halogen using radical halogenation. So you know your first step is going to be adding a radical of some sort. And now the only way we know how to get from a radical to an alkene or to a double bond is through an elimination reaction. So we know the next step is going to be some sort of E reaction to get your double bond. So in order, this is step 1, this is step 2, step 3. Now we can look at the choices that they gave us and see if we can figure it out. So the first thing I'm going to do is look at the last step, because we know that there's only one reagent that's going to give you the anti-Markovnikov addition of an OH. So I'm going to see which one of these has that. And the only option is D. So that's already looking really promising. It's probably going to be our answer, but actually you could pretty much eliminate all the other ones at this point, but let's just go in order from first. So looking at A, the issue is that they're using NBS over ROR, and NBS is only going to work when you have an alkene already on your compound. So you can eliminate A. For that same reason, you can eliminate C. Now, E, they're using F2 and heat, and that's very, very unstable and very unlikely to successfully halogenate it. So you can actually go ahead, well, all right, say we wanted to entertain F, you know, maybe you could get an F on it. Let's look at the rest of them. Then you have CH3, CH2O, sorry, this font is a little terrible, and then acid. So if you were going to use acid, you would have the generation of a carbocation, and then you would have a shift. So your OH would actually end up, let me redraw it. So if this is our starting material, your OH is going to end up, whoopsie daisies, here, and the methyl is going to move down here. So that would be your product if you used E. Say that the F did add and then the elimination did work. But unfortunately, that's not the product that we need, so you can eliminate E. Looking at B, say you monochlorinate first, okay. So now the Cl can either add here or here. because as I said before, Cl has very similar activation energies for both secondary and primary, so it's not going to be super specific. Then it's OH minus and He. Okay. So they would eliminate it that way, and then they use HCl and OH minus. His font is so terrible that it's hard for me to read it. Okay, so say that the next part is him doing the elimination reaction, but then the last step is HgSO4. So say you get your elimination product, right? Your elimination product is going to, oops, did not mean to draw the alkene there. So your elimination product is going to look like that, but then he uses HgSO4 over H2SO4, and that's the oxy-Merc reaction. So it's just one of the, I guess like that's like his shorthand version of it, but it's fine. Either way, you're going to get the more substituted addition of the OH, so that tells you that B is not going to work. And like I said, because D is the only one that had hydroboration, that's going to be the only one that gives you the anti-Markovnikov addition of the OH, so that's your right answer. Looking through it, the fact that they use Br instead of Cl or F is already a really good sign, because Br is the most stable and it's the most preferred. Then they use tert butoxide, which is going to give you the highest elimination product, because that's a very strong eliminating reagent. And then they use hydroboration. So overall, D is just the best option and the only one that's actually going to give you the correct answer. So like I said, the answer to number 9 is D. So multiple choice 11 asks, which combination of the following starting materials would result in the Diels-Alder product shown below? So this is kind of another example of retrosynthesis. You have to go back from the product and try to figure out the reagents. So the first thing I like to do is number it, going 1, 2, 3, 4, 5, 6. And the first thing I notice is that our dienophile region, this side, still has a double bond left behind. And the only way that happens is if you start with a triple bond, as you guys remember from the practice problems on the pre-mock of CN and NO2. So right off the bat, you know the dienophile has to have a triple bond in it. And the only one that has that between these is V. So you know one answer is going to include V. Okay, so you can eliminate anything that doesn't have V. Oh, not that one. So the only ones left now are B and C. So now you just have to figure out the diene format. So pulling up the template that I gave you guys before, if it's pointing away from the center, it's going to be on a dash. And if it's pointing towards the center, it's going to be on a wedge. So here we see that we have one that's on a wedge and one that's on a dash. So that means one has to be pointing away from the center and one has to be pointing towards the center. If we look at number 1, we can see that they're both pointing away from the center. But if we look at number 2, we see that one is pointing towards the center and one is pointing away from the center. This is towards, this is away. So that means our answer is going to be C with 2 and V. Oops. Hopefully that made sense to everybody. So number 12 says, which of the following are the thermodynamic and kinetic products in the addition of one equivalent of HBr to 3-methyl-2,4-hexadiene? So they showed you what the starting material looked like anyway. The first thing you have to do is figure out where you're adding your HBr. In this case, you are going to add it to this double bond because this will give you the more stable carbocation. So generating your carbocation, it's going to look like this. And this will give you your kinetic product if you use it like this. because your kinetic product is going to have the more highly substituted halogen. And then if you resonate it like this, you're going to get your thermodynamic product, because your thermodynamic product has a more highly substituted double bond. Okay, so I'll write off to the side. Actually, let me label them. Kinetic, thermo. So kinetic, more highly substituted halogen, and thermodynamic, is the more highly substituted double bond. And this will always be the case. So now that we have our kinetic and our thermodynamic drawn out, we could go look at the products or the answer choices and see which ones this matches. So our thermo looks like it's going to be number 2. Thermo. And you could see that 1 and 3 also have highly substituted double bonds. The important part is figuring out where the Br is going to go, so you actually do have to draw out the resonance for this one. And then our kinetic is going to be number 4. So our answer is going to be B. 2 is thermodynamic and 4 is kinetic. And that is the answer to number 12. Okay, so multiple choice 13 asks, which of the following correctly depicts one of the propagation steps in a radical halogen substitution reaction? So really this one is just a regurgitation of the mechanism for radical halogenation. So I'm going to go ahead and do the 2 propagation steps and using Cl and see if any of the answer choices match this. So part 1. This is already after you have your radical made, because that happens in the initiation step. Okay, so that's step 1. Step 2 is now replacing the radical with the halogen. And you use Cl2 in this step. So I would write this down and make sure you just keep these notes near you during the exam, which I'm sure most of you will probably be doing anyway. But just a reminder, because it would really be stupid not to. Alright, so now that we have the 2 steps of propagation written out, we can go ahead and compare them to the answer choices. So looking at answer choice A, we see that let me see exactly what's going on here. Okay, so apparently nothing happens to the chain. It stays exactly the same, so that's a big no-no already. And then she's using, or whoever did this, whatever, is using Cl2 directly onto the chain, which doesn't happen. In that step, you use the radical Cl, like from down here. So that's a big no-no. Moving on to answer choice B, we see that by accident, they used the radical Cl when forming the radical to Cl bond. Instead, you're going to be using Cl2 in that step. So B is no good. Looking at C, okay, apparently you start with a Cl on your chain in this one, and then you lose it, leaving a radical behind, which makes no sense because the point of the reaction is to get the Cl on the chain, so that's not correct. Looking at D, what do we have going on here? So the Cl comes and kicks the H off, kind of like elimination reaction, which definitely doesn't happen. And as you can see, they give you an H radical, which is super, super unstable and would just never happen in real life. So D is not correct. And then finally, looking at E, that does match one of our propagation steps. That matches step 1, because you have the radical Cl coming and forming and bonding with the H, leaving a radical behind on your chain. So that exactly matches our products here. So the answer to number 13 is going to be E. Okay, so number 14 asks, assuming the relative rates of radical chlorination at a certain temperature are primary equals 1, secondary equals 4, and tertiary equals 5, what is the percent yield of the reaction shown? So in our product, we see that we have a tertiary Cl. So that means the one that they're looking for is going to be the percent yield of the tertiary. But in order to do that, we have to find the relative yield for all of them. So really quickly, I'll go ahead and give you guys the equations, and then we'll just do the problem. So I'll do this in a different color. So relative amount of a specific product is equal to number of H's, or hydrogens, that can be replaced for that product times the relative rate of that type of H, whether it be primary, secondary, or tertiary. I did go over this again during the radical lecture, so if you want to go back on those notes, they might help, because this took about maybe 40 minutes to go over, so yeah, I definitely won't have enough time to do it all in this review. And then the percent yield equation, percent yield of a specific product equals the relative amount of that product over all the relative amounts combined. Oops. Times 100%. So these are the two equations that you need. So I'm going to erase now, and then we could start this actual question. Okay. So looking at it, we have to figure out how many, or the relative amount of primary H's, the relative amount of secondary H's, and the relative amount of tertiary H's that Cl can replace. So primary, secondary, tertiary. So how many H's are primary? Really quick review on what makes a primary, secondary, or tertiary H. So a primary H is basically just a terminal carbon. The H is on a terminal carbon. So these are all primary. A secondary H is on a carbon bonded to another carbon. These are secondary H's, and a tertiary H's are 3 carbons bonded together. That's a tertiary H. Okay. So let's begin. How many primary hydrogens are in this starting molecule? So we have 3 here, 3 for each of the methyls. I'm just drawing them out to show everybody exactly how many H's there are, because sometimes people forget. So for each of the 4 methyls, there are 3 H's on each of the 4. So 3 times 4 is 12. So you have 12 H's that can be replaced by a chlorine, times the relative rate of a primary H, which they gave you in the question, is 1. So 12 times 1 equals 12, and this is, okay, so let me go ahead and number of H, relative rate, and then relative amount. So that means the relative amount of primary H replacements that could happen is 12. Okay. So now we can look for secondary H's. I'm going to erase. I'll do, number of H. So I'll do secondary in purple. So we're just going to look at where the secondary hydrogens are. And the only places where we have a secondary hydrogen are here, and there's 2 of them. So 2 secondary hydrogens times the relative rate of a secondary is 4. So 2 times 4 equals 8. So that means the relative amount of secondary hydrogens is 8. And then tertiary, which is the one that we're most interested in, we'll do in a dark blue. And we have 2 tertiary H's. We have one, oops, let me redraw it. One here and one here. So 2 times the relative rate for tertiary, which is 5. So 2 times 5 is 10. So that's the relative amount of all of them. Now we have to combine these together to get the combined relative amounts of all of them. So 12 plus 8 is 20, plus 10 is 30. So 30. So then we can do the one of interest, which is tertiary. So we do 10 over 30 times 100%. And that gives you 33% yield of a tertiary hydrogen replacement via radical chlorination. So let's go ahead and look at our answer choices now. We see that B actually is 33%, so the correct answer for 14 is going to be B. If you guys had trouble with this, you can either reach out to me or check the radicals notes, because we did go over it pretty intensely over there. Okay, number 15 is a series of reaction question that actually highlights a special case or a special reaction that maybe you guys don't know or don't remember, but O'Connor may have mentioned this type of reaction in office hours. I don't remember seeing it in his notes, but we'll go through it anyway. So the first step, you're starting with a alkyne, and then you're treating it with NH2, and as we all know, that's going to create your alkynyl anion. So I'm going to go ahead and draw that out. So originally you have this H here, and then you lose it. And then they're combining your alkynyl anion with a alkyl halide. And the way that's going to react is that because the alkyl halide is electronegative, it's going to pull electrons towards itself, leaving a partial positive here. So that is going to attract these electrons to that partial positive carbon. And then that's going to kick off the Br in the process. As soon as, it kicks off the Br when the alkynyl anion attacks. So now, counting our carbons, we have 1, 2, 3, 4, 5, 6. So, 1, 2, 3, wait, let me redraw it. One, 2, 3, 4, 5, 6. Okay. I'm going to redraw it one more time because I wanted to make it a little neater than that. Yeah, so it is very important to make sure you count your carbons in these types of reactions, because otherwise you couldn't get a question wrong over something so stupid. So there we go. And then the last part is you're treating the alkyne with H2SO4 over H2O. And this is the special case. So treating alkynes with H2SO4 / H2O makes a ketone. Okay, so let's go ahead and do that. Okie dokie. So the answer to number 15 is going to be letter B. As we can see, that is the same as our product down here. Hopefully you guys write that special case down because this is really, really important. Okay, so multiple choice 17 asks, which of the following species would be present in the propagation phase of the above reaction? No, species can be present as either the reactants or as the products. So really quickly, we should go over what a peroxide is. So a peroxide is the same thing as saying ROR, which is the same thing as saying CH3, OO, CH3, or if these were ethyls or so on. Those are all different types of peroxide. Basically, it's just two oxygens bonded to carbon chains. So, generally speaking, we should go over what the HBr over ROR reaction does. So, it's going to add a Br to the less substituted side of an alkene, which is just a double bond. Oops. Okay. So now we can go ahead and go through the mechanism because I think that's the only mechanism I didn't include in these mocks. So because HBr over ROR has an interesting initiation, I will include that as well in this mech. So let's zoom in. So like I said, the first part is going to be initiation. Okay, so the first step of initiation, you're going to generate alkoxy radicals. So I'm using R, but in place of R, you can use any carbon chain. So what's going to happen is one side is going to take a radical and the other side is going to take the radical. So your product will be two alkoxy radicals. Okay, so the next step is the generation of your radical halide. So you're going to start with one of your alkoxy radicals and HBr. And what's going to happen is that the alkoxy radical is going to come and take the H, and then the other radical is going to stay on the Br, forming the radical Br. So you end up with ROH plus your radical Br. And that is the steps for initiation. I'm going to erase and then go over the two parts to propagation. Okay, so propagation, again, two parts, as they all are. So part 1 is going to be the generation of the alkyl radical and the addition of the Br to that chain. So we'll start with our Br radical. In this case, we'll use the same example from our problem. So what's going to happen is one electron from the double bond is going to form and make the bond with Br, and then one electron from the double bond is going to stay on that carbon. So you get this as your product. Okay. And then the second step of propagation is going to be getting rid of the radical using another HBr. So the radical is going to bond with the H, and then one radical is going to form another radical Br. So you'll end up with this, where the H has now come and binded here, that being this H, and then you'll have the Br radical. My lone pairs are really looking nice today. Okay, so that is the propagation, and as usual, the termination is just going to be combining all the radicals together in every way possible. I did do this exact example in the radicals notes if you want to go over the terminations, but for the sake of the mocks, I don't think he stresses termination too much, so I'm not going to spend too much time on it. So let's go ahead, now that we have our propagation, and look at which of the following species are present in the propagation stages. So we have 1 with just the radical on it, and we don't see that, so 1 is not going to be one of our answers. We have 2 with the Br on the more substituted side. Again, that's not going to be one of our answers. 3 with the Br on the less substituted. Oh my goodness, that scared me. 1 second. We have 3 with the Br on the less substituted side, and that is definitely going to be in our propagation stage because we see it here. I can't tell if that's a radical in the center or not, but even if it is, the radical version is there as well. So 3 is definitely going to be there. 4, we see a radical Br here. So 4 is there. And then HBr we see here. Br2 we do not see in the propagation stage. That's in the initiation stage. Let me get rid of the highlight. So the answer is going to be 3, 4, and 5 for 17, and that is letter E.